In this video, we'll be looking at hydride shifts and methyl or alkyl shifts. So before we get into that, it's important that you realize in chemistry, an important idea to know is that a reaction that involves a more stable intermediate is going to proceed faster than one that involves an unstable intermediate, right? And this makes sense because a stable intermediate is likely to linger or stay in the solution long enough for the reaction to proceed past the intermediate to form the product. Whereas if you have an unstable intermediate, it's more likely to revert back to the reactant, which is more stable, right, than it is to linger in solution long enough for the reaction to continue proceeding till the formation of a product, right? And we see this in the case when we were looking at Markovnikov and anti-Markovnikov products, right? The Markovnikov product is also the major product, while the anti-Markovnikov is the minor product, because, as we know, Markovnikov products are forming from the more intermediate from the more stable intermediate, right? By definition, Markovnikov products are those that form directly from the more stable intermediate, right? Which is also why they are the major product, the one that the one that forms faster and is in a higher abundance, right? Whereas the anti-Markovnikov product is the one that involves the less stable carbocation intermediate, and thus it forms the minor product. So before we continue, let's quickly solidify this idea of carbocation stability in terms of different leaving groups, or the locations of different leaving groups, right? If we have compound with the leaving group here, we can see that the loss of the leaving group would result in the formation of a tertiary carbocation, right? However, if we have the same compound with the leaving group on this carbon, for instance, the leaving group, once it leaves, would result in the formation of a secondary carbocation, which is less stable. And finally, if the leaving group was leaving from, say, this carbon, it would result in the formation of a primary carbocation, which is highly unstable. So clearly, if we had to choose, the tertiary carbocation would be the intermediate. Intermediate containing a tertiary carbocation is the one that would be more favorable and more stable compared to a secondary and obviously a primary. So let's keep this in mind and look at an example of a reaction that we've encountered before, this hydrohalogenation reaction. So if we had a compound, something that looks something like this, and we are reacting it with some hydrohalogen, we know that our pi bond is going to attack our hydrogen here, which causes these lone pairs to collapse onto, or the electrons in this bond to collapse onto the halogen as a lone pair, right? And this would lead to the formation of our molecule here, which is no longer going to be an alkene, right? We're going to have a alkane with a carbocation, and we're going to have our halogen floating in solution. But what's important to keep in mind, or what you can notice here, is that one, this is a line structure, and so there are invisible hydrogens to keep in mind, such as in this position we do have an invisible hydrogen. And what you'd notice is if our carbocation, in this case, is a secondary carbocation, if we were able to somehow have the carbocation form on this carbon, right, we would end up having a tertiary carbocation, which we know to be more stable. So how can we have this secondary carbocation somehow form a tertiary carbocation, right? So we can do this by undergoing what's called a hydride shift. So a hydride shift is, as the name would suggest, the shifting of the hydrogen that was on this tertiary carbon onto the secondary carbon here, and that would then result in us having our carbocation here, and the hydrogen would end up being on the secondary carbon. So now we have formed a more stable intermediate, a tertiary carbon containing intermediate, as opposed to this secondary carbocation containing intermediate. So now, before we move forward, let's try to take a minute to understand what is happening and why this is happening, right? If we're looking at our starting molecule here, we can see that we have a double bond between the primary carbon and the secondary carbon here. So how is it that we're able to form a carbocation on this tertiary carbon? Well, when we form this carbocation intermediate, what we'll notice is that the hydrogen that we pointed out earlier, right, is single bonded to this carbon. And what is a single bond but a pair of electrons, right? It's just a pair of electrons. And so what we'll see happening here is these electrons, along with the hydrogen itself, are going to go and attack this secondary carbocation. And so what will end up happening is we will have now this hydrogen on in place of the secondary carbocation, and we'll see that this carbon here has now lost a pair of electrons. And so this loss of electrons makes this carbon a carbocation, and we can see this again by through a quick calculation of the formal charge of this carbon. But trust me when I tell you that this now is a carbocation. And because this intermediate is more stable, this hydride shift, this going from the secondary carbocation to a tertiary carbocation through the movement of this hydrogen along with its pair of electrons, is going to happen rather quickly and in time before we have our halogen that is floating in solution can go on and attack the secondary carbocation. So we had this hydride shift occur very quickly so that in time we can have this halogen go on and attack our tertiary carbocation as the intermediate, forming this product here. Alright, now let's look at another example, one that illustrates an alkyl shift, also known as a methyl shift. So we can again undergo a hydrohalogenation reaction where we're reacting this alkene with some hydrohalogen. Let's call it HX. So once again, we'll notice that the pi electrons in the double bond will go on to attack our hydrogen, causing the electrons in this bond to collapse as a lone pair onto our halogen here. This is then going to form an intermediate, right? So very much like what we saw in the last example, we'll end up forming an intermediate that it has a secondary carbocation, right? So what we'll notice is adjacent to this secondary carbon is a quaternary carbon. This carbon here is bound to 4 other carbons. So it would form a quaternary carbocation, but what we'll see is when we have a quaternary carbocation or a quaternary carbon here, really, there is no hydrogen to undergo a shift, right? Because the carbon is bound to 4 other carbons. There is no room for a bond with a hydrogen. So what will end up happening is this entire methyl group will shift over with its pair of electrons. So the electrons that form the bond between this carbon and this carbon here, right, is going to shift entirely as we saw with the hydride shift. But again, keep in mind that when we look at this line here, this carbon at the very end also is bound to 3 hydrogens, as this is a methyl group, which is why it's called a methyl shift. So what will happen is we have this end up having, shifting over there, forming now an intermediate that looks something like this. So we end up having an entire methyl group attached to where the carbocation was. And here we have just one, and we have a carbocation, a tertiary carbocation forming. So now once again, we have our halogen floating in solution that we'll be able to go and attack, forming a product that looks something like this. So we can see that this looks rather different from our initial starting material, our reactant here, our starting alkene. So when you see something that looks rather, different with an extra methyl group, or in the other case where we have the halogen attached to a carbon that isn't even involved in the pi bond here, keep in mind or keep in your consideration that we may have either had a hydride shift or a methyl shift. So it's always important that when you're looking at the carbocation that can form, that you also keep an eye out for the carbons that are next to it, in case that you're able to form a more stable intermediate, a tertiary carbocation, as we see here. So that brings us to the end of this video. If you found it useful, please show your support by liking and subscribing. Leave any questions you may have in the comments, as well as suggestions for future videos, and I'll see you in the next one.